space holds its breath at the edge of oblivion. In the vast cosmic theatre, where galaxies dance and stars are born, there exist regions so extreme that they challenge everything we thought we knew about reality itself. These are black holes, cosmic giants, that devour light itself, bend space-time into impossible knots, and may be the universe's most profound mystery. Welcome to Whispering Universes channel, where tonight we explore one of the most tantalizing possibilities in modern physics, that the most destructive forces in the universe might also be its most creative. That these cosmic monsters, which appear to erase everything that falls into them, could actually be doorways, portals, connecting our reality to others we can barely imagine. The very name black hole suggests finality, an ending, a place where matter goes to disappear forever. Yet cutting-edge physics is revealing a different story. These gravitational titans may be nature's ultimate recycling centers, cosmic birth canals that transform the matter and energy of our universe into the seeds of entirely new realities. Where we once saw only destruction, we now glimpse creation on the grandest possible scale. This isn't science fiction, this is the frontier of theoretical physics, where Einstein's equations meet quantum mechanics in a dance so intricate it might rewrite our understanding of existence itself. Some of the brightest minds in science now seriously consider that black holes could be wormholes, connecting distant regions of space-time through shortcuts that make interstellar travel look simple. Others propose that every black hole births a new universe, making our cosmos part of an infinite family tree of realities. Tonight, we'll journey through the mathematics of impossibility, where space and time become so warped that cause and effect lose their meaning. We'll explore how information, the fundamental building blocks of reality, might survive even the most extreme gravitational crusher in the universe. We'll discover why quantum mechanics suggests that nothing can truly be destroyed, only transformed and possibly transported elsewhere. The implications stretch beyond physics into the very nature of existence itself. If black holes are indeed portals, then the matter that makes up your body, forged in the hearts of dying stars, may have traveled through cosmic gateways we're only beginning to understand. The atoms in your hand could be immigrants from another universe, cosmic refugees that found their way here through black hole tunnels spanning unimaginable distances. We'll meet the pioneers whose equations predicted these possibilities decades before we had the technology to test them. We'll explore how modern observations from gravitational wave detectors and the Event Horizon Telescope are providing the first glimpses of black hole behavior that could confirm or challenge these extraordinary theories. As you settle into this exploration, let your mind relax into possibility. Release the need for reality to behave sensibly, and prepare to follow the evidence wherever it leads, even if it leads to the conclusion that our universe is just one room in an infinite cosmic mansion, connected to countless others by tunnels we call black holes. The journey ahead will take us to the edges of known physics, where mathematics becomes poetry and the impossible begins to seem inevitable. We'll discover how the universe's most extreme environments might be nurseries for new realities, and how the information that defines your consciousness could theoretically survive. Even a journey through the cosmic furnace at a black hole's heart. So breathe deeply, let wonder fill the spaces between thoughts, and prepare to see these cosmic enigmas not as endings, but as beginnings we're only starting to comprehend. In the final moments of a massive star's life, physics writes its most dramatic script. When nuclear fusion can no longer support the stellar giant against its own crushing gravity, the star faces an inevitable collapse that creates one of the universe's most exotic objects, a black hole. This isn't just stellar death, it's the birth of a region where the normal rules of space and time cease to apply. Picture a star 20 times more massive than our Sun, burning through its nuclear fuel in mere millions of years instead of billions. When the last fusion reactions sputter out in its core, gravity wins the eternal battle it has been fighting against outward pressure. The collapse happens with stunning speed. The core shrinks from thousands of miles across to just a few miles in less than a second. This isn't gradual failure, it's catastrophic gravitational victory. The physics of this collapse pushes matter beyond all familiar limits. As the stellar core compresses, its density rises beyond anything we can directly experience on Earth. A teaspoon of this matter would weigh as much as Mount Everest. But this is just the beginning. The collapse continues, driven by gravity so intense that it overwhelms every other force in nature. At a critical point determined by what physicists call the Schwarzschild radius, something profound happens. The gravitational field becomes so strong that not even light can escape. An event horizon forms, a spherical boundary around the collapsed matter that acts as a one-way membrane. Anything crossing this boundary is forever hidden from the outside universe. From our perspective, the matter has effectively been removed from reality itself. But black holes come in different varieties, each with its own personality shaped by how it formed. Stellar mass black holes, born from collapsed stars, typically contain between 3 and 20 times our Sun's mass, compressed into a region smaller than Manhattan. Intermediate black holes, still mysterious in their origins, might form from the collision of smaller black holes or through other exotic processes we don't yet understand. Then there are the supermassive giants lurking at galactic centers, cosmic monsters containing millions or billions of solar masses. These titans likely formed in the early universe through processes that remain hotly debated. Some may have grown from smaller black holes that merged and fed voraciously on surrounding matter. Others might have formed directly from the collapse of massive gas clouds in the infant cosmos, bypassing the stellar phase entirely. What makes black holes truly strange isn't just their immense gravity, it's how they warp the fabric of spacetime itself. Einstein showed us that mass and energy curve the geometry of space and time like a bowling ball, creating a depression in a stretched rubber sheet. Black holes take this curvature to its absolute extreme, creating what mathematicians call a singularity, a point where the curvature becomes infinite and our equations break down completely. Near a black hole's event horizon, time itself becomes distorted in ways that challenge intuition. As you approach the boundary, time dilation becomes so extreme that you would experience hours while outside observers see millennia pass. This isn't science fiction, it's a direct consequence of Einstein's general relativity, confirmed by countless experiments and observations. The discovery of Hawking radiation in the 1970s added another layer of mystery to these cosmic enigmas. Stephen Hawking showed that quantum mechanics predicts black holes should actually emit radiation, slowly evaporating over astronomical timescales. This radiation appears to be perfectly thermal, carrying no information about what fell into the black hole. This creates what physicists call the information paradox, one of the deepest unsolved problems in theoretical physics. If information about the matter that falls into black holes is truly destroyed, it would violate one of the most fundamental principles of quantum mechanics, that information is always conserved. This principle underlies our understanding of how physical processes can be reversed, even in principle. The information paradox suggests either that our understanding of quantum mechanics is incomplete, or that black holes don't actually destroy information, perhaps by acting as portals that transfer it elsewhere. Modern observations have transformed black holes from purely theoretical objects to astronomical realities we can study directly. Gravitational wave detectors have recorded the collisions of black holes across cosmic distances, while the Event Horizon Telescope has given us actual images of the event horizon around the supermassive black hole in galaxy M87. Each new observation brings us closer to understanding whether these cosmic giants are truly dead ends or cosmic gateways to realities beyond our current imagination. As stellar matter disappears behind event horizons around the universe, we're left with a profound question: where does it go? The mathematics suggests several possibilities, each more extraordinary than the last. To understand how black holes might function as portals, we must first grasp how they fundamentally alter the structure of reality itself. Einstein's field equations, the mathematical heart of general relativity, predicted the existence of these space-time distortions decades before astronomers found evidence for actual black holes. These equations reveal that matter and energy don't just exist in space-time, they actively reshape it, creating geometric features that can be as dramatic as they are counterintuitive. The simplest black hole solution to Einstein's equations was discovered by Carl Schwarzschild in 1916, just months after Einstein published his theory. Working on the Russian front during World War I, Schwarzschild solved the equations for the space-time geometry around a spherically symmetric, non-rotating mass. Tragically, he died of an autoimmune disease contracted during the war, never knowing that his solution would become one of the most important discoveries in theoretical physics. The Schwarzschild solution reveals space-time geometry so warped that it defies everyday experience. As you approach a black hole, space becomes increasingly curved, like moving deeper into a funnel. At the event horizon, this curvature reaches a critical threshold. The geometry becomes so distorted that all paths through spacetime, even those followed by light, curve inexorably inward toward the central singularity. But most black holes in the real universe aren't perfectly spherical and motionless. Stars rotate, and this rotation doesn't disappear when they collapse. In 1963, Roy Kerr solved Einstein's equations for rotating black holes, discovering geometry even stranger than Schwarzschild's static case. A rotating black hole drags spacetime around with it, in a phenomenon called frame dragging, creating a region called the ergosphere, where nothing can remain stationary relative to distant observers. This rotation fundamentally changes the black hole's structure. Instead of a single event horizon, rotating black holes possess two, an outer horizon and an inner horizon. The space between these boundaries has properties so exotic that physicists still debate what could survive there. Some theories suggest this region might be where the portal properties of black holes become most apparent. The Kerr geometry also predicts something remarkable. It might be possible to extract energy from a rotating black hole through the Penrose process, proposed by physicist Roger Penrose in 1969. By dropping specially prepared objects into the ergosphere, you could theoretically extract rotational energy from the black hole itself, causing it to spin more slowly while gaining energy in the process. This isn't just theoretical. Astrophysicists believe this mechanism powers some of the most energetic phenomena in the universe, including the relativistic jets that shoot from active galactic nuclei. But perhaps the most intriguing feature of black hole geometry lies in what mathematicians call the maximally extended solution. When you solve Einstein's equations completely, without making assumptions about what's physically reasonable, something unexpected emerges. The geometry doesn't end at the black hole's center, it continues, connecting to other regions of spacetime that could be entirely separate universes. This mathematical discovery reveals what physicists call an Einstein-Rosen bridge, more commonly known as a wormhole. In the complete mathematical description, a black hole in our universe connects to a white hole in another universe, a hypothetical object that spits out matter and energy instead of consuming it. The black hole and white hole are two ends of a tunnel through the higher dimensional structure that underlies our apparently three-dimensional reality. The inner horizon in rotating black holes creates even stranger possibilities. Beyond this boundary, the normal relationship between space and time becomes scrambled in ways that allow for closed, time-like curves, paths through space-time that loop back on themselves. While this might seem to permit time travel, most physicists believe that quantum effects or other physical principles prevent such paradoxes from actually occurring. Recent mathematical work has revealed that black hole interiors might be far more complex than previously imagined. Instead of containing a single central singularity, some solutions suggest the possibility of multiple connected regions, each potentially corresponding to different universes or different regions of our own universe. These aren't science fiction speculations, they're direct mathematical consequences of Einstein's equations when pushed to their logical extremes. The geometry inside black holes might also help resolve the information paradox. If black hole interiors connect to other regions of spacetime, information that appears to be destroyed from our perspective might actually be preserved elsewhere. The mathematics suggests several ways this could work, each involving connections between different regions that could span cosmic distances, or even bridge to entirely separate realities. Modern computational techniques allow physicists to simulate black hole mergers and explore their geometry in unprecedented detail. These simulations reveal how spacetime itself ripples and tears during the collision of black holes, creating gravitational waves that carry information about the most extreme gravitational environments in the universe. Each simulation teaches us more about how these cosmic architects reshape reality's very foundations. As we peer deeper into black hole geometry, we discover that these objects might be far more than gravitational monsters. They could be cosmic infrastructure wormholes, connecting distant regions, white hole factories birthing new universes, or quantum computers processing information on scales we can barely comprehend. What would you actually experience if you fell into a black hole? This question has fascinated physicists for decades, because the answer reveals profound truths about the nature of space, time, and information itself. Your journey past the event horizon would be unlike anything else in the universe, a one-way trip through increasingly warped space-time that challenges our most basic assumptions about reality. As you approach a stellar mass black hole feet first, the first thing you'd notice is tidal force, the difference in gravitational pull between your head and feet. Since gravity weakens with distance, your feet, being closer to the black hole, experience stronger gravitational acceleration than your head. For a black hole containing a few solar masses, this differential becomes extreme quite rapidly, stretching your body vertically while compressing it horizontally in a process physicists grimly term spaghettification. But let's imagine instead that you're approaching a supermassive black hole, where the tidal forces near the event horizon are surprisingly gentle. The Schwarzschild radius of such giants can be larger than Mercury's orbit around the Sun, spreading the gravitational gradient over such vast distances that you might cross the event horizon without immediate physical distress. This counterintuitive fact that bigger black holes are gentler reveals how space-time geometry scales in unexpected ways. The most profound aspect of your fall isn't physical but temporal. From your perspective, falling toward and through the event horizon happens in a finite amount of your proper time. You check your watch, feel time passing normally, and cross what seems like an invisible boundary in space. Nothing special marks the moment you pass through. There's no wall, no barrier, just continuing freefall through increasingly curved space-time. But observers watching your descent from a safe distance see something entirely different. As you approach the event horizon, they witness your image slowing down, your movements becoming sluggish, your light shifting redward as gravitational time dilation becomes extreme. From their perspective, you never quite reach the event horizon. Your image freezes there, growing dimmer and redder as the light you emit stretches to longer and longer wavelengths until it fades from view entirely. This dramatic difference in perspectives, you experiencing a normal crossing while external observers see you frozen, illustrates one of general relativity's most mind-bending features. There's no absolute simultaneity, no universal now that determines when events really happen. Your crossing of the event horizon is real from your reference frame, but never occurs from the external reference frame. Both perspectives are equally valid descriptions of the same physical situation. Once inside the event horizon, your experience becomes even stranger. In the Schwarzschild geometry, all paths lead inexorably toward the central singularity, where tidal forces grow infinite and space-time curvature diverges. You have a finite amount of proper time before reaching this geometric endpoint, perhaps minutes for a stellar mass black hole, or hours for a supermassive one. However, recent theoretical developments suggest your actual experience might be radically different. The firewall paradox, proposed in 2012, argues that black holes might possess a wall of high-energy particles just inside the event horizon. If this firewall exists, you would be incinerated instantly upon crossing the boundary, resolving certain quantum mechanical paradoxes at the cost of violating the equivalence principle that underlies general relativity. Alternative theories propose even more exotic possibilities. Some suggest that black hole interiors might be far larger than the exterior. Geometry suggests vast spaces that could accommodate entire universes' worth of matter and energy. Others propose that the singularity itself might be traversable, connecting to other regions of space-time through wormhole-like passages that preserve information and matter. The holographic principle adds another layer of mystery to your fall. According to this idea, all the information about your physical structure might be encoded on the black hole's two-dimensional event horizon surface. From this perspective, you never actually enter the black hole's interior. Instead, your information content becomes part of the horizon's holographic description, while your physical body is destroyed at the boundary. String theory suggests even more radical possibilities. In some string theoretical models, what appears to be the black hole interior might actually be a fuzzball, a complex, the extended object made of fundamental strings and brains rather than empty space leading to a singularity. If this picture is correct, your fall might involve interaction with this exotic matter structure rather than a journey through empty space-time. Recent work in quantum error correction has proposed that black hole interiors might function as cosmic computers, processing quantum information in ways that preserve unitarity. while appearing to destroy information from an external perspective. In these models, your fall becomes a computational process where your quantum state is encoded, processed, and potentially transmitted elsewhere through quantum mechanical channels. Perhaps the most intriguing possibility is that your journey doesn't end at the singularity, but continues through to other regions of spacetime. The mathematical solutions to Einstein's equations suggest that black hole interiors might connect to white hole regions where matter and energy emerge rather than disappear. Your fall through a black hole might be the first leg of a cosmic journey that deposits you in another universe entirely. The question of what you would experience has profound implications for our understanding of information, consciousness, and the nature of physical law itself. If information cannot be destroyed, as quantum mechanics suggests, then your fall must preserve every quantum bit that defines your physical and mental state. This preservation might happen through mechanisms we don't yet understand, possibly involving connections to other universes or encoding schemes that spread your information across vast cosmic networks. As theoretical physics grapples with these possibilities, one thing becomes clear. Falling into a black hole might not be an ending, but a transformation we can barely begin to comprehend. In 1974, Stephen Hawking made a discovery that forever changed our understanding of black holes and launched what physicists now call the information war, a decades-long battle over fundamental principles that continues to reshape theoretical physics. Hawking showed that black holes aren't perfectly black. Instead, they emit radiation and slowly evaporate, creating a paradox that strikes at the heart of quantum mechanics and general relativity. The discovery emerged from Hawking's investigation of quantum field theory near black hole event horizons. In the quantum world, what we think of as empty space actually teems with virtual particle pairs, ephemeral fluctuations that normally appear and annihilate each other so quickly that they can't be directly observed. But near a black hole's event horizon, these quantum fluctuations behave differently. Picture virtual particle pairs materializing just outside the event horizon. Normally, these pairs would quickly recombine and disappear back into the quantum vacuum. But the black hole's intense gravitational field can separate them before they reunite. One particle falls past the event horizon, while its partner escapes to infinity as real radiation. The black hole loses a tiny amount of mass energy to power this escaping radiation, growing fractionally smaller with each emitted particle. This Hawking radiation has a temperature inversely related to the black hole's mass. Stellar mass black holes emit radiation so cold, trillions of times colder than the cosmic microwave background, that they actually absorb more energy from their surroundings than they emit. But smaller black holes burn hotter, and hypothetical microscopic black holes would radiate furiously, evaporating in brilliant flashes of energy. The temperature relationship creates a peculiar feedback effect. As a black hole evaporates and loses mass, its temperature increases, causing it to radiate faster and lose mass even more quickly. This runaway process means that black hole evaporation accelerates exponentially in its final stages. A stellar mass black hole would take longer than 1067 years to evaporate, completely far longer than the current age of the universe. But its final moments would release the energy equivalent of millions of hydrogen bombs in a fraction of a second. What makes Hawking radiation deeply problematic isn't its existence, but its apparent properties. When Hawking calculated the quantum state of the radiation, he found it to be perfectly thermal random, carrying no information about the matter that originally fell into the black hole. This creates what Leonard Susskind later named the information paradox. The paradox strikes at a fundamental principle of quantum mechanics, unitarity, which states that information can never be destroyed, only scrambled or rearranged. If you burn a book, quantum mechanics insists that all information about the book's contents remains encoded in the exact arrangement of smoke particles, ash, and radiated energy. With sufficient knowledge and computational power, you could theoretically reconstruct the book's contents from these remnants. But Hawking's calculation suggested that black holes violate this principle. When matter falls into a black hole and the black hole later evaporates through Hawking radiation, the thermal nature of the radiation seems to erase all information about the original matter. From the radiation alone, you couldn't determine whether the black hole had consumed encyclopedias, elephant DNA, or exotic matter from another galaxy. This violation of unitarity would have profound consequences for physics. It would mean that quantum mechanics, our most successful theory for describing the fundamental behavior of matter and energy, breaks down in the presence of gravity. It would also suggest that information could genuinely disappear from the universe, making physics inherently unpredictable in ways that go far beyond quantum mechanical uncertainty. The information paradox sparked intense debate among physicists. Some, including Hawking initially, accepted that information might indeed be destroyed in black holes, requiring modifications to quantum mechanics. Others, led by Gerard Hooft and Leonard Susskind, insisted that information must be preserved somehow, even if the mechanism wasn't immediately apparent. Various solutions have been proposed over the decades. Some suggest that Hawking radiation isn't truly thermal, but contains subtle correlations that encode information about the black hole's contents. Others propose that information escapes through exotic channels, perhaps wormholes, connecting the black hole interior to distant regions of spacetime, or through holographic encoding on the event horizon surface. The firewall proposal, introduced in 2012 by Ahmed Al-Mehri and colleagues, suggested a radical resolution. They argued that preserving information requires the formation of a highly energetic firewall at the event horizon that incinerates anything attempting to cross. This solution saves unitarity but violates Einstein's equivalence principle, which states that freely falling observers shouldn't experience anything special when crossing an event horizon. Recent developments in quantum error correction have provided new insights into potential solutions. These approaches suggest that black hole evaporation might function like a quantum error correcting code, where information about the black hole's contents is gradually transferred to the outgoing Hawking radiation through quantum entanglement mechanisms too subtle to detect with current technology. The holographic principle offers another perspective on the information paradox. If the black hole's interior is merely a holographic projection of information stored on the two-dimensional event horizon, then information never truly enters the black hole. It's always encoded on the boundary surface. From this viewpoint, the information paradox dissolves because information was never really inside the black hole to begin with. Perhaps the most intriguing possibility is that the information paradox reveals something profound about the nature of spacetime itself. Recent work suggests that spacetime might be an emergent property of quantum entanglement patterns. In this picture, black holes don't destroy information, but redistribute it through quantum networks that span cosmic distances, possibly connecting to other universes through mechanisms we're only beginning to understand. The information war continues, with new theoretical weapons deployed regularly. Each proposed solution reveals deep connections between gravity, quantum mechanics, and information theory that hint at a more fundamental understanding of reality itself. Whether black holes destroy information or preserve it through exotic mechanisms, the answer will reshape our understanding of the universe's deepest principles. In 1935, Albert Einstein and Nathan Rosen made a discovery that would haunt physics for decades and inspire countless science fiction stories. While studying the mathematical structure of black holes, they found that Einstein's field equations naturally produce bridges connecting distant regions of spacetime, cosmic shortcuts that could theoretically allow travel between separated parts of the universe, or even between different universes entirely. The Einstein-Rosen bridge emerges from the complete mathematical solution to Einstein's equations for a black hole. When physicists solve these equations without making assumptions about what's physically reasonable, they discover that black hole geometry extends far beyond what we can observe from the outside. The spacetime continues through the black hole's interior and emerges into another region, creating a tunnel-like structure connecting two separate areas of space and time. To visualize this bridge, imagine spacetime as a flat rubber sheet. A black hole creates a deep funnel extending downward through the sheet. But the mathematical solution doesn't end at the bottom of this funnel. Instead, the geometry continues, emerging as an upward funnel on the other side of the sheet. The result resembles an hourglass or tunnel connecting two separate universes, with the narrow waist at the point where the two event horizons meet. This connected geometry reveals something profound about the nature of black holes. What appears from our perspective to be a one-way gravitational trap might actually be one end of a cosmic bridge. Matter and energy that disappear into black holes don't necessarily reach a dead-end singularity. They might emerge elsewhere through the corresponding white hole, a hypothetical object that spits out matter and energy instead of consuming it. The mathematics of these bridges is elegant, but reveals immediate practical problems. Einstein-Rosen bridges, in their simplest form, are extraordinarily unstable. Any attempt to send matter or information through the bridge causes it to collapse so rapidly that nothing can traverse it. The bridge pinches off faster than light can travel through it, making it useless as a practical tunnel between distant regions. This instability arises from the bridge's extreme sensitivity to matter and energy. Even a single photon attempting to cross triggers gravitational effects that cause the bridge's throat to contract and seal. The mathematics shows that keeping an Einstein-Rosen bridge open would require exotic matter with negative energy density, a theoretical possibility allowed by quantum mechanics, but never observed in macroscopic quantities. Despite these obstacles, physicists haven't abandoned the idea of traversable wormholes. In 1988, Kip Thorne and Michael Morris showed that certain modifications to the basic Einstein-Rosen bridge could create stable, traversable shortcuts through spacetime. These theoretical wormholes would require threading the bridge's throat with exotic matter possessing negative energy density, but they could remain open indefinitely and allow two-way travel. The exotic matter requirements for stable wormholes push the boundaries of known physics. Quantum field theory does predict the existence of negative energy densities. In certain circumstances, the Casimir effect demonstrates this on microscopic scales. However, quantum inequalities appear to limit how much negative energy can be concentrated in any region, making macroscopic wormholes extremely difficult to construct and maintain. Recent theoretical work has explored whether naturally occurring wormholes might exist in the universe. Some models suggest that wormholes could form during the early universe's inflationary period, when extreme energy densities and rapid expansion might create the exotic conditions necessary for stable bridges. These primordial wormholes could potentially survive to the present day, hidden from direct observation but detectable through their gravitational effects. Another possibility is that advanced civilizations might learn to construct and maintain artificial wormholes using technologies we can barely imagine. The energy requirements would be staggering, comparable to the mass energy of entire stars, but the physics doesn't absolutely forbid such engineering projects. The construction of a traversable wormhole would represent the ultimate achievement in space-time manipulation. The relationship between Einstein-Rosen bridges and black holes takes on new meaning in light of recent developments in string theory and quantum gravity. Some string theoretical models suggest that what we perceive as black holes might actually be highly curved regions of higher dimensional space, where the apparent event horizon is just a projection of more complex geometry existing in dimensions we can't directly access. These higher dimensional perspectives open possibilities for wormhole-like connections that don't require exotic matter in the traditional sense. Instead, the exotic properties might arise from the geometry of extraspatial dimensions, allowing bridges to form and persist through mechanisms that bypass the classical stability problems. Such wormholes might be abundant in the universe but difficult to detect because their connections involve dimensions beyond our three-dimensional experience. The holographic principle adds another layer of possibility to wormhole physics. If spacetime itself is an emergent property of quantum information networks, then Einstein-Rosen bridges might represent fundamental connections in the underlying information structure. These bridges wouldn't be tunnels through space in the traditional sense, but direct quantum links between distant regions, mediated by entanglement patterns that span cosmic distances. Recent work in quantum error correction has revealed deep connections between wormhole geometry and quantum computation. Some theorists propose that traversable wormholes might function as quantum computers, processing information in ways that preserve unitarity while allowing faster-than-light information transfer between their endpoints. This could resolve certain paradoxes in black hole physics while opening entirely new possibilities for cosmic-scale information processing. The search for observational evidence of Einstein-Rosen bridges remains one of the most challenging frontiers in astrophysics. Wormhole mouths might be detectable through their gravitational effects on nearby matter or through the unique patterns of light deflection they would create. Some researchers have proposed that certain unexplained astronomical phenomena, such as gamma-ray bursts or fast radio bursts, might originate from matter emerging through wormhole connections. As our mathematical understanding of space-time geometry deepens, Einstein-Rosen bridges continue to reveal new possibilities for cosmic connection and travel. Whether they exist in nature or remain purely theoretical constructs, these bridges challenge our assumptions about the separateness of distant regions and suggest that the universe might be far more interconnected than we ever imagined. One of the most mind-bending discoveries in modern physics emerged not from studying particles or forces, but from contemplating the information capacity of black holes. The holographic principle, the idea that all information contained within a volume of space can be encoded on its boundary surface, fundamentally challenges our assumptions about the nature of space, dimensionality, and reality itself. This principle suggests that what we experience as three-dimensional reality might be a projection from information stored on a distant, two-dimensional surface. The journey toward this revolutionary insight began in the 1970s, when Jacob Bekenstein and Stephen Hawking discovered that black holes possess entropy proportional to the area of their event horizons rather than their volume. This was profoundly unexpected. In ordinary thermodynamic systems, entropy typically scales with volume. The more space available for particles to occupy, the more ways they can be arranged. But black holes seem to follow different rules. Bekenstein realized that black hole entropy must be related to information storage capacity. If you drop a book into a black hole, the black hole's entropy increases by an amount that depends on the information content of the book. This led to the remarkable conclusion that a black hole's information storage capacity is finite and proportional to the area of its event horizon surface, not its volume. The implications were staggering. If black hole entropy represents maximum possible information density, then no region of space can contain more information than what could be encoded on its boundary surface. This suggested something radical. Perhaps the information we think exists throughout three-dimensional space is actually stored on two-dimensional boundaries, with our three-dimensional experience being a kind of holographic projection. The holographic principle gained concrete mathematical form through the work of Leonard Susskind and Gerard Hooft in the 1990s. They proposed that quantum gravity theories in higher dimensions are equivalent to quantum field theories living on lower dimensional boundary surfaces. This wasn't just a mathematical curiosity, it suggested that our perception of spatial dimensionality might be fundamentally mistaken. The principle received dramatic confirmation through Juan Maldacena's 1997 discovery of AD-CFT correspondence, a precise mathematical relationship between string theories in curved spacetime and conformal field theories on the boundary of that spacetime. This correspondence showed that certain gravitational theories in 5 dimensions are exactly equivalent to gauge theories in 4 dimensions, providing the first concrete example of holographic duality in action. For black holes, the holographic principle implies something extraordinary. All the information about matter that falls into a black hole might never actually enter the 3-dimensional interior. Instead, this information could be encoded holographically on the black hole's 2-dimensional event horizon surface. From this perspective, the black hole's interior doesn't exist as an independent 3-dimensional space, but emerges as a holographic projection of information patterns on the boundary. This holographic encoding resolves the information paradox in an elegant but counterintuitive way. Information doesn't disappear when matter falls into black holes, because the information never actually enters the black hole's interior. It's absorbed into the holographic description on the event horizon surface. As the black hole evaporates through Hawking radiation, this information is gradually released back into the external world through subtle correlations in the outgoing radiation. The encoding mechanism might work through quantum error correction principles. The event horizon acts like a quantum error correcting code, redundantly storing information across multiple quantum degrees of freedom on the surface. Even if parts of this encoding are corrupted or lost, The redundancy ensures that the original information can be reconstructed from the remaining pieces. Recent work has revealed deep connections between holographic encoding and quantum entanglement. The geometric structure of spacetime might emerge from entanglement patterns between quantum degrees of freedom to living on boundary surfaces. In this picture, the black hole's interior geometry is generated by entanglement correlations between different regions of the event horizon, creating an emergent three-dimensional space from fundamentally two-dimensional information. This entanglement-based understanding of geometry has led to remarkable insights about the nature of space itself. Einstein's equations might not be fundamental laws of physics, but emergent consequences of quantum entanglement patterns. Spacetime curvature would then represent the geometry of entanglement networks, with black holes arising naturally from highly entangled quantum systems. The holographic principle also suggests new ways to think about what happens when black holes merge. When two black holes spiral into each other and coalesce, their individual event horizons merge into a single, larger surface. From the holographic perspective, this process involves the merger of two separate quantum information processing systems into a unified system with greater information capacity. Gravitational waves ripples in spacetime produced by accelerating masses take on new meaning in the holographic framework. These waves might represent perturbations in the holographic encoding itself, carrying information about how quantum entanglement patterns change as massive objects move through space. The detection of gravitational waves thus provides direct access to the dynamics of holographic information processing on cosmic scales. The principle has profound implications for our understanding of consciousness and perception. If the three-dimensional reality we experience is holographically encoded on distant boundaries, then our consciousness might be accessing this holographic information through mechanisms we don't yet understand. The subjective experience of depth, space, and separation between objects could all emerge from information processing patterns on two-dimensional surfaces. Some theorists propose that the boundary surfaces encoding our reality might be located at the cosmic horizon, the boundary beyond which we cannot receive information due to the expansion of the universe. In this model, all of observable reality would be a holographic projection from information encoded on this distant cosmic boundary, making our entire universe a kind of cosmic hologram. The holographic principle has also inspired investigations into whether information can be transmitted through black holes via quantum teleportation protocols. If black hole interiors are holographic projections of boundary information, then quantum states might be teleportable between the exterior and interior through entanglement-based communication channels that don't require physical matter to cross the event horizon. As we delve deeper into the holographic nature of reality, we discover that black holes might be the universe's ultimate information processors, cosmic computers that encode, process, and output information through mechanisms that transcend our traditional understanding of space and time. The event horizon becomes not a barrier to information, but a cosmic display screen projecting reality itself. In the quantum realm, distance becomes meaningless in ways that confounded even Einstein. Quantum entanglement, the mysterious connection between particles that allows them to instantly influence each other across any distance, has emerged as a key to understanding how black holes might function as cosmic portals. This spooky action at a distance, as Einstein skeptically called it, may provide the fundamental mechanism by which information and possibly matter can traverse the vast spaces between black holes and their connected regions. Quantum entanglement occurs when two or more particles become correlated in such a way that measuring one instantly determines the properties of its partners, regardless of the distance separating them. This isn't communication in the traditional sense. No information travels between the particles faster than light. Instead, the particles share a quantum state that transcends spatial separation, existing as a unified system even when its components are separated by cosmic distances. Bell's theorem, proven by physicist John Stuart Bell in 1964, demonstrated that these quantum correlations are stronger than any classical physical theory allows. Experiments have confirmed that entangled particles violate Bell inequalities, mathematical relationships that any local realistic theory must satisfy. This means either that quantum mechanics allows faster than light influences, violating special relativity, or that particles don't possess definite properties independent of measurement, challenging our notion of objective reality. The resolution lies in understanding that entanglement doesn't transmit information, but reveals pre-existing correlations that transcend classical spacetime. When you measure an entangled particle and instantly know the state of its distant partner, you're not receiving information from across space. You're accessing non-local correlations that exist outside the normal framework of space and time. For black holes, quantum entanglement opens extraordinary possibilities. If particles can maintain quantum correlations across cosmic distances, then matter falling into black holes might remain entangled with particles outside, creating quantum bridges that preserve information even when classical communication becomes impossible. These entanglement bridges could function as cosmic internet connections, linking different regions of the universe through quantum channels. The ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind in 2013, makes this connection explicit. They suggested that quantum entanglement, EPR, after Einstein, Podolsky, and Rosen, and Einstein-Rosen bridges, ER, the original name for wormholes, are the same phenomenon viewed from different perspectives. Every pair of entangled particles might be connected by a microscopic wormhole, and every wormhole might represent a quantum entanglement between its two mouths. This identification transforms our understanding of both entanglement and spacetime geometry. Wormholes would no longer be exotic spacetime structures requiring bizarre matter, they would be natural consequences of quantum entanglement. Conversely, quantum entanglement would gain geometric meaning as actual connections through higher dimensional space. The implications for black hole physics are profound. When matter falls into a black hole, its quantum state might remain entangled, with Hawking radiation escaping from the black hole's exterior. This creates what physicists call the firewall paradox. If information is truly preserved through entanglement, then the structure of entanglement around black holes becomes so complex that it might create a wall of high-energy particles at the event horizon. Recent work has shown that resolving the firewall paradox requires understanding how entanglement networks create emergent spacetime geometry. The black hole's interior might not exist as an independent region, but might emerge from entanglement patterns between the outgoing Hawking radiation and a distant quantum system connected to the black hole through cosmic scale. Entanglement networks. Quantum teleportation protocols, demonstrated in laboratories worldwide, show how quantum information can be transmitted instantaneously across space using entanglement. The process doesn't transport particles themselves, but transfers their quantum states through entangled channels. For black holes, this suggests that information falling past event horizons might be instantaneously teleported to other regions of the universe through entanglement connections we're only beginning to understand. The monogamy of entanglement, the quantum mechanical principle that limits how entanglement can be shared between multiple systems, creates additional constraints on black hole information processing. A quantum system can be maximally entangled with, at most, one other system, limiting the complexity of entanglement networks that can form around black holes. This constraint might explain why black holes appear to have finite information processing capacity and why they emit thermal radiation. String theory provides frameworks for understanding how quantum entanglement might operate on cosmic scales. In string theoretical models, fundamental particles are one-dimensional objects whose vibrations create the properties we observe. These strings can be entangled across vast distances, creating networks that span multiple universes and connect different regions of the cosmic landscape through quantum channels. The holographic principle reveals how entanglement might encode three-dimensional geometry on two-dimensional surfaces. The pattern of quantum entanglement between different regions of a boundary surface might determine the geometric properties of the emergent three-dimensional space. Black holes, with their highly entangled quantum states, might create complex interior geometries through entanglement patterns we're only beginning to map. Recent experiments in quantum information theory have demonstrated that entanglement can be used to perform computations that are impossible with classical physics. Quantum computers use entanglement to process information in ways that scale exponentially with the number of entangled quantum bits. Black holes, with their vast numbers of entangled degrees of freedom, might function as the universe's ultimate quantum computers, processing cosmic-scale information through entanglement networks. The relationship between entanglement and time provides another piece of the puzzle. Some theories suggest that time itself might emerge from quantum entanglement patterns, with the flow of time representing the evolution of entanglement correlations. In black holes, where time dilation becomes extreme, these entanglement time relationships might create temporal bridges that allow information to flow between different epochs in cosmic history. As quantum technology advances, we're developing new tools for creating and manipulating entanglement on larger scales. Laboratory experiments with thousands of entangled particles are revealing how quantum correlations behave in complex systems. These studies provide insights into how cosmic-scale entanglement networks might operate, bringing us closer to understanding whether black holes truly function as quantum portals connecting distant regions of space and time. The universe might be far more connected than classical physics suggests, with quantum entanglement providing invisible threads that link black holes to white holes, different regions of our universe to each other, and possibly our entire cosmos to other realities beyond our current perception. When mathematicians solve Einstein's field equations completely, without imposing restrictions based on what seems physically reasonable, they discover something remarkable about black hole interiors. Rather than ending at a singular point of infinite density, the geometry continues indefinitely, revealing multiple asymptotic regions that could represent entirely separate universes. This mathematical structure, known as the eternal black hole, or maximally extended Schwarzschild solution, suggests that black holes might be cosmic doorways connecting our reality to an infinite network of other realities. The eternal black hole emerges when physicists consider the complete analytical extension of black hole spacetime. Instead of assuming that matter collapsed to form the black hole at some finite time in the past, this solution describes a black hole that has existed forever and will exist forever, hence, eternal. This mathematical idealization reveals geometric features hidden in more realistic collapse scenarios. The extended solution contains 4 distinct regions. Our universe, the region where we can potentially observe the black hole from the outside, represents just one of these regions. There's also the black hole interior, which we've already explored, plus a second exterior region that looks much like our own universe, but is causally disconnected from it. Most intriguingly, there's a 4th region that represents the interior of what physicists call a white hole, a hypothetical object that spits out matter and energy instead of consuming it. White holes are the time-reversed versions of black holes, permitted by Einstein's equations but never observed in nature. Where a black hole's event horizon prevents anything from escaping, a white hole's horizon prevents anything from entering. Matter and energy would pour out of white holes continuously, but nothing could ever fall in to fuel this emission. The mathematics suggests that white holes are highly unstable. Any slight perturbation would cause them to collapse into black holes. In the eternal black hole geometry, the white hole region connects directly to the black hole interior through a bridge-like structure. This Einstein-Rosen bridge provides a pathway from our universe's black hole to the white hole in the POW, disconnected exterior region. Matter falling into the black hole could theoretically traverse this bridge and emerge from the white hole in the other universe. However, the bridge in the eternal solution has a crucial limitation. It's non-traversable. The geometry evolves dynamically, and the bridge connecting the black hole and white hole regions expands to maximum size and then contracts to 0 in a finite amount of coordinate time. This contraction happens so rapidly that no signal, not even light, can traverse the bridge before it pinches off completely. The non-traversability arises from the extreme instability of the bridge structure. Even infinitesimally small perturbations cause the bridge to collapse faster than anything can cross it. This suggests that, while the mathematical structure permits connections between different universes, practical traversal might be impossible due to the dynamic nature of the geometry. Despite these limitations, the eternal black hole solution has inspired numerous theories about cosmic connectivity. Some physicists propose that rapidly rotating black holes, described by the Kerr solution rather than the simpler Schwarzschild case, might possess more stable bridge structures. The rotation could potentially provide stabilizing effects that keep traversable pathways open for longer periods. The Kerr solution introduces additional complexity through its multiple event horizons. A rotating black hole possesses both an outer and inner horizon, with exotic properties in the region between them. Some solutions suggest that pathways through rotating black holes might lead not to white holes, but to other regions of our own universe, creating cosmic shortcuts that could enable faster-than-light travel between distant locations. Recent work in string theory and quantum gravity has revealed that black hole interiors might be far more complex than even the extended classical solutions suggest. Some string theoretical models describe black hole interiors as containing entire universes worth of space, with geometries that expand indefinitely rather than contracting to singularities. These bag of gold models propose that black holes might be cosmic nurseries where new universes gestate and develop. The holographic principle adds another layer of mystery to eternal black hole structure. If the black hole interior is holographically encoded on the boundary, then the multiple regions revealed by analytical extension might represent different ways of decoding the same boundary information. The other universe connected through the Einstein-Rosen bridge might not be a separate reality, but an alternative description of information patterns that also encode our own universe. Quantum mechanics further complicates the picture by introducing uncertainty into the geometric structure itself. The classical notion of a definite spacetime geometry might break down in quantum gravity, replaced by quantum superpositions of multiple possible geometries. The eternal black hole might exist in a quantum superposition of states that includes traversable bridges, non-traversable bridges, and configurations where bridges don't exist at all. Some theoretical frameworks suggest that the multiple regions of eternal black holes might represent parallel branches of quantum mechanics itself. Each region could correspond to a different outcome of quantum measurement processes, with the Einstein-Rosen bridge providing connections between parallel quantum realities. In this interpretation, black holes become cosmic quantum computers that process information about alternative histories and parallel possibilities. The relationship between eternal black holes and cosmology opens even more speculative possibilities. Some models propose that our entire universe might have emerged from the interior of a black hole in a previously existing universe. The Big Bang could represent the moment when matter and energy from a parent universe began emerging through a white hole connection, seeding the space and time that would eventually contain galaxies, stars, and planets. This cosmological black hole hypothesis suggests that universe creation might be an ongoing process throughout the cosmic landscape. Every black hole could potentially birth new universes, creating an infinite tree of connected realities, where each universe contains black holes that spawn additional universe branches. Our cosmos would be just one leaf on this infinite tree of creation. The search for observational evidence of eternal black hole structure remains one of the most challenging problems in theoretical physics. The multiple regions are separated by event horizons that prevent direct communication, making it seemingly impossible to detect whether the connected regions actually exist. However, subtle quantum effects might provide indirect evidence through correlations in Hawking radiation or other quantum mechanical signatures. As our understanding of black hole physics deepens, the eternal black hole solution continues to reveal new possibilities for cosmic connection and creation. Whether these mathematical structures represent physical realities or merely theoretical curiosities, they challenge our assumptions about the isolation and finitude of our universe. The dream of traversable wormholes has captivated physicists for decades, evolving from pure mathematical curiosity to serious theoretical engineering problem. While naturally occurring Einstein-Rosen bridges collapse too quickly to allow passage, modern theoretical physics has identified potential solutions that could create stable, traversable shortcuts through spacetime. These advances suggest that sufficiently advanced civilizations might eventually construct artificial wormholes, turning science fiction dreams into engineering realities. The breakthrough came in 1988, when Kip Thorne and Michael Morris, working with student Matt Visser, identified the specific requirements for traversable wormholes. Their analysis showed that stable wormholes require exotic matter with negative energy density, the matter that creates repulsive gravitational effects rather than the attractive gravity we normally experience. This exotic matter must thread the wormhole's throat, holding it open against the natural tendency for Einstein-Rosen bridges to collapse. Exotic matter isn't pure fantasy. Quantum field theory predicts its existence in specific circumstances. The Casimir effect, demonstrated in laboratories worldwide, creates regions of negative energy density between closely spaced conducting plates. Virtual particles in the quantum vacuum create pressure that pushes the plates together, effectively generating negative energy density in the space between them. While these effects are minute, they prove that exotic matter can exist in principle. The energy requirements for macroscopic wormholes are staggering. To create a wormhole throat large enough for human passage would require negative energy comparable to the mass of Jupiter, concentrated in a region smaller than an atomic nucleus. Extending this throat across interstellar distances would require even more exotic matter, distributed throughout the wormhole's length to maintain stability against gravitational collapse. Quantum inequalities impose additional constraints on exotic matter configurations. These theorems, derived from quantum field theory, limit how much negative energy can be concentrated in any region and for how long. The inequalities suggest that large amounts of negative energy can exist only briefly, or small amounts can exist for longer periods. This creates a fundamental tension between the stability requirements for traversable wormholes and the quantum mechanical limits on exotic matter. Despite these obstacles, theoretical physicists have identified several potential workarounds. Some proposals involve dynamically maintained wormholes where the exotic matter configuration changes rapidly to stay within quantum inequality bounds while maintaining traversability on average. Others suggest using quantum field manipulations to create temporarily traversable windows that allow passage before quantum effects force the wormhole to close. String theory has opened new possibilities for wormhole engineering by providing frameworks where exotic matter emerges naturally from higher dimensional physics. In some string theoretical models, what appears as negative energy density in our three-dimensional space might actually represent normal matter configurations in the higher dimensional spaces where strings vibrate. This could make exotic matter abundant in the universe while remaining difficult to detect directly. The relationship between wormholes and quantum entanglement has inspired entirely new approaches to wormhole construction. If the ER equals EPR conjecture is correct, that wormholes and quantum entanglement are the same phenomenon, then creating traversable wormholes might be equivalent to engineering specific quantum entanglement patterns. This could make wormhole construction a quantum information processing problem rather than a classical engineering challenge. Quantum teleportation protocols already demonstrate how information can traverse space instantaneously through entanglement channels. Scaling these protocols to macroscopic objects would require creating and maintaining enormous entanglement networks, but the fundamental physics appears to allow such scaling. Advanced civilizations might build cosmic-scale quantum networks that function as distributed wormhole systems, allowing instantaneous travel between network nodes. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, shares mathematical similarities with traversable wormholes. Both concepts require exotic matter to function, and both allow effective faster-than-light travel without violating special relativity. Recent work has shown that Alcubierre drives and wormholes might be mathematically equivalent descriptions of the same underlying spacetime manipulation technology. Modern proposals for wormhole engineering often involve combinations of exotic matter, advanced quantum field manipulation, and spacetime engineering techniques that push the boundaries of known physics. Some concepts require civilizations capable of manipulating matter and energy on galactic scales, while others might be achievable with more modest technological advances in quantum field control. The energy economics of wormhole construction remain daunting. Creating a single traversable wormhole might require harnessing the energy output of entire stars for extended periods. Maintaining the wormhole against quantum fluctuations and gravitational perturbations would require ongoing energy investment comparable to stellar luminosities. Only civilizations with access to cosmic-scale energy sources could seriously attempt such projects. However, the benefits of successful wormhole engineering would be transformative. A network of traversable wormholes would effectively shrink the universe, allowing instantaneous travel between distant galaxies and enabling communication across cosmic distances without delay. Such networks could support galactic civilizations that span multiple galaxy clusters, united by wormhole highways that transcend the limitations of ordinary spacetime. Recent advances in metamaterial engineering and quantum field manipulation have brought some aspects of wormhole physics closer to experimental investigation. While we can't yet create macroscopic wormholes, researchers are beginning to construct analog systems that reproduce some aspects of wormhole physics in laboratory settings. These experiments provide insights into the fundamental physics that would govern real wormhole behavior. The search for naturally occurring traversable wormholes continues alongside theoretical engineering efforts. Some astrophysical phenomena remain unexplained and might represent signatures of natural wormhole activity. Fast radio bursts, gamma-ray bursts, and certain types of gravitational wave signals could potentially originate from matter transiting through cosmic wormholes. Artificial intelligence and machine learning are beginning to contribute to wormhole research by identifying new solutions to Einstein's field equations that might permit stable, exotic matter configurations. These computational approaches can explore vast parameter spaces of possible wormhole geometries, potentially discovering configurations that satisfy both stability requirements and quantum constraints. As our understanding of quantum gravity deepens, the boundary between impossible and merely difficult continues to shift. Wormhole engineering represents the ultimate expression of space-time manipulation technology, the ability to reshape the very fabric of reality to serve cosmic engineering purposes. Whether such capabilities remain forever theoretical or eventually become practical achievements may depend on discoveries we have yet to make about the deepest principles governing space, time, and matter. The question of whether black holes truly function as portals to other universes has moved beyond pure theory into the realm of observational astronomy. Modern instruments are becoming sensitive enough to detect the subtle signatures that might distinguish portal-like black holes from conventional gravitational monsters. These signatures could appear in gravitational waves, electromagnetic radiation patterns, or exotic particle emissions that reveal hidden connections to other regions of spacetime. Gravitational wave detectors like LIGO and Virgo have revolutionized our ability to study black holes by detecting the ripples in spacetime created when massive objects accelerate. These waves carry information about the internal structure and dynamics of their sources, potentially revealing whether black holes possess the complex interior geometry predicted by portal theories. The gravitational wave signatures from wormhole-connected black holes might differ subtly from those of conventional black holes in ways we're only beginning to understand. When two black holes spiral toward each other and merge, their gravitational waves follow specific patterns predicted by general relativity. However, if these black holes are actually wormhole mouths connected to other regions of spacetime, the merger dynamics might be modified by feedback effects from the connected regions. Matter or energy flowing through the wormhole connections could alter the orbital dynamics, creating detectable variations in the gravitational wave frequency evolution. The final moments of black hole mergers might reveal the most dramatic portal signatures. If merged black holes maintain connections to other universes, the newly formed black hole might exhibit unusual settling behavior as it adjusts to modified boundary conditions imposed by its wormhole connections. This could appear as unexpected gravitational wave emissions continuing long after conventional theory predicts the system should have quieted down. The Event Horizon Telescope has provided our first direct images of black hole event horizons, revealing the shadow cast by the supermassive black hole in Galaxy M87 and later in our own Milky Way's center. These images might contain hidden signatures of portal activity. Matter flowing through wormhole connections could create asymmetries in the accretion disk, or unusual patterns in the hot gas surrounding the black hole that differ from conventional models. Wormhole-connected black holes might exhibit distinctive electromagnetic signatures in their accretion disks, the swirling rings of hot matter spiraling into the black hole. If matter can flow through wormhole connections, we might observe unexpected correlations between black holes in different parts of the universe, with material disappearing from one black hole's accretion disk appearing around its connected partner. This would create distinctive spectral signatures and timing correlations across cosmic distances. The polarization patterns of light from black hole environments could reveal portal signatures. When light passes through the strongly curved spacetime near a black hole, its polarization becomes rotated in ways that depend on the detailed geometry. Wormhole connections might create additional geometric features that modify these polarization patterns, creating detectable differences from conventional black hole predictions. Hawking radiation, though incredibly faint for astrophysical black holes, might carry signatures of portal activity. If black holes are connected through wormholes or holographic networks, the quantum correlations in Hawking radiation might be different from those predicted for isolated black holes. Future quantum technologies might become sensitive enough to detect these correlation patterns, providing the first direct evidence of quantum entanglement across cosmic distances. High-energy cosmic rays and gamma rays could provide another window into portal physics. If exotic matter or energy flows through wormhole connections, it might create high-energy particle emissions with distinctive spectral characteristics. These emissions could appear as unexplained gamma-ray bursts, ultra-high-energy cosmic ray events, or other energetic phenomena that don't match conventional astrophysical models. Gravitational lensing effects around black holes might reveal portal signatures through subtle modifications to the way light bends around these massive objects. Wormhole connections could alter the spacetime geometry in ways that create distinctive lensing patterns, potentially detectable through precision observations of background stars and galaxies. These effects might be most pronounced for rotating black holes, where frame dragging creates additional geometric complexity. Time delay measurements could provide evidence of portal activity by revealing unexpected correlations between black holes across the universe. If black holes are connected through networks of wormholes or quantum entanglement, events at one black hole might influence behavior at connected black holes, with time delays that depend on the nature of the connections rather than the speed of light travel between them. The search for primordial black holes, hypothetical objects formed in the early universe, might reveal portal signatures if these objects formed with wormhole connections intact. Primordial black holes could possess exotic properties not found in black holes formed from stellar collapse, potentially including stable wormhole connections that create detectable astronomical signatures. Advanced interferometry techniques are being developed to search for exotic spacetime oscillations that might reveal hidden dimensions or wormhole connections. These experiments could detect minute periodic variations in spacetime geometry that would appear if black holes are connected through higher dimensional structures that oscillate or vibrate at characteristic frequencies. Machine learning algorithms are increasingly used to analyze astronomical data for subtle patterns that might escape human notice. These systems could identify correlations between black hole behaviors across the universe that would be invisible to conventional analysis, but might reveal the quantum entanglement networks predicted by portal theories. Future space-based gravitational wave detectors like LISA will be sensitive to low-frequency gravitational waves that could carry signatures of cosmic-scale wormhole activity. These detectors might observe the gravitational wave equivalents of wormhole weather, fluctuations in space-time geometry caused by matter and energy flowing through cosmic portal networks. Quantum sensing technologies under development might eventually become sensitive enough to detect the quantum field fluctuations predicted around wormhole mouths. These sensors could search for regions of space where quantum field properties differ from vacuum expectations in ways that would indicate the presence of exotic matter or hidden spacetime connections. As observational capabilities continue advancing, we're entering an era where portal theories can be tested through direct observation rather than purely theoretical analysis. The next decade may bring the first definitive evidence of whether black holes are merely gravitational dead ends or cosmic gateways connecting our universe to realities beyond our current imagination. One of the most profound implications of black hole portal theories is the possibility that our entire universe might have emerged from the interior of a black hole in a previously existing cosmos. This concept, known as cosmological natural selection or the fecund universe hypothesis, suggests that black holes serve as cosmic reproduction organs, giving birth to new universes through processes that could explain some of the most puzzling features of our own reality. The idea began with physicist Lee Smolin's observation that the fundamental constants of physics in our universe seem remarkably well tuned for the formation of stars, galaxies, and ultimately black holes. If these constants were even slightly different, the universe might contain no stars at all, or stars might burn out too quickly to forge the heavy elements necessary for complex chemistry. This fine-tuning puzzle has long challenged cosmologists who wonder why nature chose values that permit such rich cosmic evolution. Smolin proposed that universes might undergo a form of natural selection, with those capable of producing many black holes having more offspring universes, and therefore becoming more common in the cosmic landscape. Each time a black hole forms, the enormous energies and extreme spacetime curvature at its center might trigger the birth of a new universe through processes similar to cosmic inflation. This new universe would initially be microscopic, but would rapidly expand to cosmic proportions through inflationary mechanisms. The daughter universe wouldn't replace or destroy the parent cosmos. Instead, it would exist in its own separate spacetime, connected to the parent universe only through the black hole that birthed it. From the perspective of observers in the parent universe, the daughter universe would be forever hidden behind the black hole's event horizon. But from within the daughter universe, observers would see their own Big Bang and cosmic evolution, unaware of their black hole origins. This reproduction mechanism could explain why our universe's physical constants are so well suited for black hole formation. If universes that efficiently produce black holes have more offspring, then the cosmic landscape would gradually become dominated by universes with physics similar to our own. The apparent fine-tuning wouldn't be coincidental, but would result from evolutionary pressure, favoring universes that maximize black hole production. The hypothesis makes specific predictions about how physical constants should be distributed across the multiverse. Parameters that affect stellar evolution and black hole formation, such as the strength of nuclear forces or the mass of fundamental particles, should be close to optimal for maximizing black hole production. Constants that don't significantly affect black hole formation might vary more randomly across different universes. Recent work in string theory has provided theoretical frameworks for how black hole-spawned universes might actually form. Some string theoretical models describe black hole interiors as regions where the normal rules of spacetime break down and new cosmic structures can emerge. These baby universe scenarios show how quantum fluctuations in black hole interiors might seed new inflationary regions that evolve into separate universes. The relationship between black hole mass and universe properties adds another layer to the theory. Larger black holes might spawn larger or longer-lived universes, while smaller black holes could produce universes with different physical properties. This suggests that the multiverse might contain a vast ecosystem of universe types, each adapted to different physical environments and evolutionary pressures. Quantum mechanics introduces additional complexity through the many worlds interpretation, which suggests that quantum measurements split reality into parallel branches. If black hole formation involves quantum processes, as it surely does, then each black hole might spawn not just one daughter universe, but an entire quantum multiverse of parallel realities, each exploring different quantum outcomes from the black hole formation process. The holographic principle provides yet another perspective on black hole universe creation. If three-dimensional spacetime emerges from information encoded on two-dimensional surfaces, then new universes might form when black hole event horizons develop sufficient complexity to encode multiple universe descriptions simultaneously. The birth of daughter universes would represent phase transitions in the holographic information processing occurring on black hole boundaries. Observational tests of the fecund universe hypothesis are extraordinarily challenging because daughter universes are hidden behind event horizons. However, the theory makes statistical predictions about the distribution of black hole masses and formation rates that might be testable through astronomical surveys. If our universe is optimized for black hole production, we should observe black hole formation rates and mass distributions that maximize total black hole output over cosmic time. The hypothesis also predicts that universes capable of supporting intelligent observers should typically be near optimal for black hole production. This creates a testable relationship between the existence of life and the efficiency of black hole formation that distinguishes cosmological natural selection from other explanations for fine-tuning. Some theoretical models suggest that information about parent universe properties might be transmitted to daughter universes through quantum channels that transcend the event horizon barrier. If this information transfer occurs, then civilizations in daughter universes might eventually decode messages from their parent cosmos, revealing the cosmic family tree that connects different realities. The energy source for universe creation remains an open question. Creating a new universe requires enormous amounts of energy, comparable to the mass energy of the black hole itself. Some models propose that this energy comes from the gravitational binding energy released during black hole formation, while others suggest that vacuum energy fluctuations in curved spacetime provide the necessary power. Advanced civilizations might eventually learn to trigger artificial universe creation by engineering black holes with specific properties designed to optimize daughter universe characteristics. This cosmic engineering could involve creating black holes with precisely controlled mass, spin, and charge to produce universes with desired physical properties or enhanced habitability. The ethical implications of universe creation are staggering. If black hole formation spawns new universes containing billions of sentient beings, then astrophysical processes that create black holes become acts of cosmic creation on scales difficult to comprehend. The responsibility of advanced civilizations capable of controlling black hole formation would extend far beyond their own universe to the countless beings and realities they bring into existence. The fecund universe hypothesis transforms black holes from cosmic destroyers into cosmic creators, suggesting that the universe's most extreme objects might also be its most generative. If the theory is correct, then our own universe represents one leaf on an infinite tree of realities, each universe spawning new branches through the black holes it creates. We would be part of a vast cosmic family, connected to parent and sibling universes through bonds stronger than light and deeper than space itself. The fate of information in black holes represents one of the deepest puzzles in physics, with implications that extend far beyond gravity to touch the very foundations of reality, consciousness, and cosmic purpose. If information truly cannot be destroyed, as quantum mechanics insists, then black holes must either preserve information through exotic mechanisms or violate one of the most fundamental principles of physical law. The resolution of this puzzle may reveal that black holes function as cosmic recycling centers, transforming the information content of matter and energy into new forms that transcend our current understanding. Information, in the physicist's sense, is far more fundamental than data stored on computer drives or words printed in books. It encompasses every quantum property that distinguishes one particle from another, every correlation between distant systems, every pattern that makes one state of matter distinguishable from any other. When quantum mechanics declares that information cannot be destroyed, it means that the complete quantum state of any system must always remain recoverable, even if scrambled or encoded in unrecognizable forms. This principle underlies our understanding of physical reversibility. In principle, any physical process can be run backwards if you have perfect knowledge of the final state and unlimited computational resources. When you burn a book, quantum mechanics insists that all information about the book's contents remains encoded in the exact positions and quantum states of every smoke particle, ash fragment, and photon of radiated heat. While practically impossible, the book could theoretically be reconstructed by reversing the combustion process with perfect precision. Black holes challenge this principle by appearing to destroy information completely. When matter falls past an event horizon, it seems to vanish from our universe forever. If the black hole later evaporates through Hawking radiation, the thermal nature of that radiation appears to carry no information about what originally fell in. From Hawking radiation alone, you couldn't determine whether the black hole had consumed hydrogen, plutonium, or the complete works of Shakespeare. Recent theoretical developments suggest several ways that black holes might preserve information while appearing to destroy it. The holographic principle proposes that information never actually enters the black hole's three-dimensional interior, but becomes encoded on the two-dimensional event horizon surface. From this perspective, information preservation is guaranteed because the information was never inside the black hole to begin with. It was always encoded holographically on the boundary. Quantum error correction provides another framework for understanding how black holes might preserve information. These mathematical techniques, originally developed for quantum computing, show how information can be redundantly encoded across multiple quantum systems in ways that survive partial corruption or loss. Black hole event horizons might function as cosmic quantum error-correcting codes, encoding information about infalling matter across vast numbers of quantum degrees of freedom in ways that ensure perfect recoverability. The black hole complementarity principle developed by Leonard Susskind and colleagues, suggests that information preservation depends on your perspective. From the viewpoint of an outside observer, information remains encoded on the event horizon surface and is eventually released through Hawking radiation. From the perspective of an infalling observer, information proceeds normally into the black hole interior. These apparently contradictory descriptions are both correct. They represent complementary views of the same physical reality, much like wave-particle duality in quantum mechanics. Recent work on the black hole interior structure suggests even more exotic information preservation mechanisms. Some theoretical models propose that black hole interiors contain vast amounts of space, potentially infinite regions where information can be stored and processed indefinitely. These bag-of-gold models transform black holes from information destroyers into information preservers on cosmic scales, maintaining perfect records of everything that ever fell past their event horizons. The ER equals EPR conjecture provides yet another avenue for information preservation by connecting black holes to other regions of spacetime through quantum entanglement. If black holes are wormhole mouths connected to distant regions, then information falling into black holes might be transmitted through these connections rather than being destroyed. The information would emerge elsewhere in the universe, or possibly in other universes entirely, maintaining perfect preservation while appearing locally destroyed. Digital physics interpretations of quantum mechanics suggest that information might be the most fundamental constituent of reality, more basic than matter or energy. In these frameworks, particles and forces emerge from underlying information and processing patterns, making information preservation an absolute requirement for physical consistency. Black holes would necessarily preserve information because destroying information would be equivalent to destroying reality itself. Cosmic recycling through black holes might operate on multiple levels simultaneously. At the quantum level, information about particle properties and field configurations could be preserved through holographic encoding and quantum error correction. At larger scales, information about complex structures, planets, stars, civilizations might be encoded in patterns spanning multiple black hole systems connected through entanglement networks. The relationship between information and consciousness adds profound dimensions to black hole information preservation. If consciousness emerges from specific information processing patterns, as many theories suggest, then the preservation of information through black hole processes might also preserve aspects of consciousness that survive physical death. The information content that defines individual identity could potentially be recovered from black hole radiation or transmitted through wormhole connections to other regions of spacetime. Advanced civilizations might eventually learn to exploit black hole information preservation for cosmic engineering purposes. Instead of viewing black holes as destructive forces, they might use them as information compression and transmission systems, encoding vast amounts of data in holographic patterns on event horizon surfaces or transmitting information across cosmic distances through wormhole networks. Time-reversed black hole processes suggest that information preservation might involve temporal as well as spatial recycling. White holes, the time-reversed versions of black holes, would emit matter and energy in perfectly correlated patterns that reconstruct everything that ever fell into their corresponding black holes. This temporal recycling could operate across cosmic timescales, with information from the early universe being preserved and re-emitted in highly processed forms billions of years later. Quantum computation perspectives on black hole information processing reveal how these objects might function as the universe's ultimate information processors. With vast numbers of quantum degrees of freedom and processing timescales that can span cosmic epochs, black holes could perform computations impossible for any finite classical system. The information falling into black holes might emerge in highly processed forms that represent solutions to cosmic-scale computational problems. The cosmic implications of perfect information preservation through black holes transform our understanding of meaning and purpose in the universe. If no information is ever truly lost, then every thought, every discovery, every moment of consciousness that has ever existed remains encoded somewhere in the cosmic information matrix. Black holes become not destroyers but preservers, maintaining perfect cosmic memory that transcends individual death and cosmic catastrophe. As we probe deeper into the quantum structure of spacetime, black holes reveal themselves as far more than gravitational monsters. They emerge as cosmic librarians, quantum computers, information recycling centers, and possibly gateways to realms of existence we've barely begun to imagine. Have journeyed through the most extreme regions of spacetime, where the familiar laws of physics stretch to their breaking point, and reality reveals possibilities that challenge every assumption about the nature of existence. Black holes, once thought to be cosmic graveyards, where matter goes to die, have emerged as perhaps the universe's most creative forces. Potential portals connecting distant regions of space and time, cosmic birth canals spawning new realities, and quantum computers processing information on scales that dwarf human imagination. The mathematics leads us to conclusions that seem impossible, yet appear increasingly inevitable. Einstein's equations, when pushed to their logical extremes, describe wormholes connecting separate universes. Quantum mechanics, our most successful theory of matter and energy, suggests that information can never be destroyed, only transformed and transmitted through channels we're only beginning to understand. The holographic principle reveals that our three-dimensional reality might emerge from information patterns encoded on distant cosmic boundaries. These aren't merely theoretical curiosities confined to the blackboards of physics departments. Gravitational wave detectors are beginning to probe the quantum structure of spacetime itself. The Event Horizon Telescope provides direct images of the shadows cast by these cosmic giants. Advanced quantum technologies are approaching the sensitivity needed to detect the subtle correlations that might reveal hidden connections between black holes across cosmic distances. The implications stretch far beyond physics into the deepest questions of existence itself. If black holes truly function as portals, then the matter composing your body forged in stellar cores and dispersed through supernova explosions might have traveled through cosmic gateways spanning unimaginable distances. The atoms in your hand could be cosmic immigrants from other universes, refugees from realities whose physics we can barely imagine. The information that defines your consciousness, encoded in the quantum patterns of neural activity, might possess a form of cosmic immortality through black hole preservation mechanisms. The holographic principle suggests that every thought, every memory, every moment of awareness becomes part of the universe's permanent information matrix, encoded in patterns that transcend individual death and cosmic catastrophe. If the fecund universe hypothesis proves correct, then our cosmos represents one branch on an infinite tree of realities, each universe spawning new branches through the black holes it creates. We would be part of a vast cosmic family, connected to parent and sibling universes through bonds deeper than space and stronger than gravity itself. Every black hole in our universe might nurture new realities, where different versions of physics create entirely alien forms of matter, energy, and consciousness. The universe reveals itself as far stranger and more wonderful than our ancestors could have imagined. These cosmic furnaces that appear to consume everything in their path might actually be nature's ultimate recycling centers, transforming matter and information rather than destroying it. Where we once saw endings, cutting-edge physics reveals beginnings. Where we once perceived isolation, quantum mechanics reveals connection. Where we once assumed destruction, mathematics discovers creation. The search for truth about black holes continues, driven by humanity's deepest need to understand our place in the cosmic story. Each gravitational wave detection, each quantum correlation measurement, each theoretical breakthrough brings us closer to answering questions that touch the very foundations of reality. Are we alone in an isolated universe, or connected to infinite others through hidden pathways? Does consciousness end with death, or does information preservation ensure a form of cosmic continuity we're only beginning to understand? As you drift into sleep, let these questions gently accompany your journey into unconsciousness. Allow yourself to imagine floating freely through the curved space-time around massive black holes, experiencing the dilation of time, witnessing the stretching of space itself. Picture the vast networks of quantum entanglement that might connect every particle in your body to others scattered across cosmic distances. Feel yourself as part of an infinite web of information and possibility that transcends the boundaries of individual existence. In the morning, you will wake in the same physical universe, governed by the same physical laws. But perhaps your sense of isolation will have diminished. Perhaps the boundaries between self and cosmos will seem less absolute. Perhaps you will carry with you a deeper sense of connection to the cosmic processes that created the atoms in your body, the photons entering your eyes, and the quantum fields permeating the space around you. The black holes that seem so alien and threatening reveal themselves as cosmic architects, builders of bridges between realities we have yet to explore. In their event horizons, we glimpse the boundaries of knowledge itself. In their singularities, we encounter the limits of current understanding and the promise of discoveries yet to come. In their quantum radiation, we find hints of information preservation mechanisms that might extend the story of consciousness far beyond what we previously thought possible. These cosmic giants invite us to expand our conception of reality itself, to embrace possibilities that stretch the boundaries of imagination while remaining grounded in the mathematics of physical law. They challenge us to see destruction as transformation, isolation as hidden connection, and endings as beginnings we have yet to understand. Thank you for joining this exploration of the universe's most extreme phenomena. May these cosmic mysteries inspire continued wonder about the reality we inhabit and the realities that might lie beyond the event horizons of our current understanding. Until next time, keep questioning the infinite and sleep peacefully among the stars.